Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VJEC Institute of Engineering Technology. As part of Dynamics of Machinery course, today we are going to discuss a concept on partial balancing of locomotives. As we have seen, unbalanced forces, how they arise, we have taken crank, single slider crank mechanism, and we have seen the effect of that. Now considering locomotives, you need to understand basic configuration of locomotives. Locomotives, basically there are two types, coupled and uncoupled. Coupled in the sense that two or more wheels are coupled together. The reason is to increase adhesive force between the wheels and track. Then these type of these type of locomotives are called coupled locomotives. Otherwise, if there are no coupling of wheels, then it is uncoupled locomotive. Okay, generally these locomotives have two cylinders. It consists of inside cylinder locomotives and outside cylinder locomotives. Inside cylinder locomotives, cylinders are mounted between wheels. It is called inside cylinder locomotive. Means wheels are outside the cylinder. Cylinders are in between wheels. Outside locomotives, vice versa. Cylinders are outside the wheels. Wheels are in between cylinders. Okay. In general, the cranks of these two cylinders are set at 90 degrees apart each other, so that engine can start easily after stopping in any position. So balance masses on wheels in any type of locomotive. So the balancing masses placed on wheels only in any type of locomotive. In coupled locomotive, wheels are coupled by connecting their crank pins with coupling rods. How they are connected? Crank pins with coupling rods. As the coupling rods revolve with the crank pin, its proportionate mass can be considered as revolving mass, which can be completely balanced. So in uncoupled locomotives, there are four planes of consideration. While analyzing balancing masses, we need to consider four planes in case of uncoupled locomotives. Two planes are in cylinders, located, and two of them are wheels located. In coupled locomotives, there are 6 planes. Why? The coupling rods also have different planes. That means these 6 planes are 2 of cylinders, 2 of coupling rods, and 2 of wheels. The planes which contain the coupling rod masses lie outside the planes that contain the balance masses. So balance masses, coupling rod masses lies outside the balancing masses. Of course, balancing masses on wheels we are going to cap. Also, in case of coupled locomotives, the mass required to balance the reciprocating parts is distributed among all the wheels. Mass always on wheels which are coupled. These results in reduced hammer blow. As we know that effect of partial balancing of reciprocating masses, in case of locomotives also, these three phenomena exist. In case of partial balancing, means some unbalanced forces are remain. These effects are hammer blow, variation tractive effect, swaying couple. As you know that hammer blow is the maximum vertical unbalanced force, the force which is perpendicular to the line of stroke, caused by the mass provided to balance the reciprocating masses. Whatever mass you are keeping to balance them, opposing the opposite direction to the crank with some radius, then that leads to vertical component, perpendicular component in the line of action. The maximum magnitude of this vertical component, vertical unbalanced force, causes hammer blow. So as we know that its value is mb r omega square. As you know that mb is mass kept for balancing. Omega is crank rotation angular velocity. Thus it varies as the square of the speed. At high speeds, because m r omega square, mb r omega square, at high speeds, the force of the hammer blow could exceed the static load on the wheels, and the wheels can lift it off. This is hammer blow is basically mb r omega square. The partial amount of mass which is kept for balancing, that is mb. So fraction of the mass c into m. M is mass of reciprocating reciprocating parts. So mb r omega square. It is square of the speed, it is variation, hammer blow. At high speeds, obviously, the force of hammer blow is exceed the static load on the wheels, and the wheels can be lifted off the rail when the direction of the hammer blow will be vertically upward. Downward it will contact with the wheels, upward direction, then it is lifted off the wheels, because crank is rotating. As we know that vertical component is in general for crank angle of theta mb or omega square sin theta. So theta 90 or 270. So if it is direction vertically upward, this magnitude maximum at 90 degrees of crank angle, then obviously it is lifted off the rails. That means the wheels will lifted off from the rails. Okay, anyhow. Now coming to the second one, variation of tractive force. You know that tractive force is the force of an engine caused by unbalanced portion of the primary force, which acts along the line of the stroke of the locomotive engine. Let us consider C is the fraction of the mass which is going to be balanced out of M mass of reciprocating parts. Then there are two cylinders, as we have seen. These two cylinders cranks are kept 90 degrees each other. Just discussed. Now coming to unbalanced force on each cylinder. First cylinder, primary force per cylinder 1. It is obviously, because C is the fraction of mass balanced, 1 minus C is remain out of balance. That means unbalanced. That is mr omega square cos theta. We are talking about primary forces. Okay. So this is omega is not there. Okay. Cos theta. Then unbalanced primary force for cylinder 2. What is cylinder 2? This is theta plus 90. Instead of theta, that crank is placed theta plus 90 mr omega square cos theta plus 90. Okay. So this becomes minus 1 minus c mr omega square sin theta. Okay. Minus 1 minus c mr omega square sin theta. Okay. Then if you see that total unbalanced primary force or variation in the tractive force is sum of these two. Okay. So this can be written as 1 minus c times, what is this? This is total unbalanced primary force or variation in the tractive force, because it is along the line of stroke. So this is okay, total tractive effect, that is force mr omega square into, this is cos theta, and second one is 1 minus c mr omega square minus sin theta. Okay, this is. Then if we want when this is becoming maximum, then obviously we know that mathematically cos theta minus sin theta term in the brackets, which should be become maximum. For what value of theta it is going to be maximum, we know that mathematically we can have d by d theta of cos theta minus sin theta. Okay, then this must be equal to 0. Then we get condition of theta at which the unbalanced, that is tractive effort force, is maximum. So we can differentiate this. Cos theta is minus sin theta, okay, and minus cos theta, okay, equal to 0. Then we can have sin theta equal to minus cos theta, right? Then tan theta equal to minus 1. So what is the theta value? Theta we have two values. Tan theta minus 1 means second quadrant and fourth quadrant. Second quadrant means tan theta minus 1 gives theta is 135 or okay plus 180, 315. Okay, these are two values. Now try to substitute these values and find this term cos theta minus sin theta. So we have unbalanced forces 1 minus c mr omega square cos theta minus sin theta. 1 minus c mr omega square cos theta minus sin theta. Cos 135. Let us see at theta equal to 135. What is this magnitude? Sin 135. So you know that cos 135 is minus 1 by root 2. Sin 135 is okay 1 by root 2. So it is, you are going to get, this is 1 minus c into mr omega square. Okay. So you are going to get minus root 2 overall, minus root 2 1 minus c, right, mr omega square. Okay. Similarly, if you see that at theta equal to 315, at theta equal to 315, similar way you substitute and see that you are going to get this maximum magnitude of this reactive effect is 1 minus C mr omega square, okay, plus root 2 you will get, plus root 2, okay. So the maximum variation of the tractive effect is, you will have plus or minus, these are two values, depends on, okay, plus or minus root 2 into 1 minus C, okay, mr omega square. So this is the quantity here mentioned, plus or minus root 2 1 minus C mr omega square is the maximum variation in the tractive force. The cylinders are kept and the cranks are oriented 90 degrees each other, cylinder 1 and cylinder 2. Okay, this is the magnitude. Okay, then now second effect, swaying couple. So unbalanced primary force along the line of stroke, as just we have seen that is plus or minus, that is 1 minus C mr omega square into cos, okay, theta. Second one is cos theta plus 90. So two cylinders. So this is the one unbalanced force, 1 minus C mr omega square, okay, cos theta. Second one, because this is the unbalanced force direction. Second cylinder, this is, you have seen, minus 1 minus C mr omega square, okay, sin theta minus, okay, second force. Then along the center line of the engine, okay, if you take moments, then you are going to get, okay, this is length, central distance between the cylinders is L, let us say. Then you can write moment about the center line, 1 minus mr omega square cos theta L by 2, this is clockwise. Similarly, it is minus of 1 minus C mr omega square sin theta into L by 2. That is the total couple. This couple is called unbalanced primary. This couple is the tends to make the leading wheels sway from side to side, because this is perpendicular to this line of stroke. Okay, this couple perpendicular to the line of stroke. Okay, so this tends to make the leading wheels sway from side to side. Okay, swaying couple, you write that this swaying couple magnitude, this is L by 2, okay, cos theta minus of 1 minus C mr omega square sin theta. Obviously, you are going to get 1 minus C, okay, here also L by 2, okay, L by 2. So, L into 1 minus C mr omega square cos theta plus sin theta, cos theta plus sin theta. When this becomes again maximum, then it's obviously from simple mathematics, d by d theta of, if you differentiate cos theta plus sin theta term, this should be become maximum. So differentiate with respect to theta and make it equal to 0. Then you will have tan theta, you will get the condition tan theta equal to 1, similar to previous one. You will get tan theta equal to 1. Then theta is at 45 or third quadrant, 180 plus 45, 225. These two values you will get maximum. Then substitute this value theta, okay, 45 once, and again see at 225 what is this maximum value of this unbalanced swaying couple. Then you will have, you get plus or minus 1 by root 2 1 minus C mr omega square L. L is distance between the cylinders. I think you are able to understand. This is the magnitude. What is this? Plus or minus 1 by root 2 into 1 minus C mr omega square L. This is the magnitude of, maximum magnitude of swaying couple. Okay, it's very clear. Tractive effect you have plus or minus root 2 1 minus C mr omega square, and this is the tractive effect plus or minus root 2 1 minus C mr omega square, and swaying couple is plus or minus 1 by root 2 1 minus C mr omega square L. This is the couple, that is the force. Okay, then coming to secondary balancing. What happens secondary balancing masses? Okay, we have seen primary masses are the crank is making an inclination theta, and it is r is the length, it is rotating with angular velocity omega. Then secondary forces, you can have consider the imaginary crank which is rotating, okay, angle 2 theta, imaginary crank 2 theta means here it will get this, and this rotating with 2 omega angular velocity, and crank length is r by 4n if you write. Okay, then you can see primary is mr omega square cos theta, primary forces of, okay, inertia forces. Secondary is, you know that, mr omega square cos 2 theta by n. Okay, you can modify and write the secondary forces equation such that, okay, if you write mr 2 omega square cos 2 theta by 4n you will get. Okay, that component of this force along line of stroke is secondary force, is secondary unbalanced force is mr 2 omega square cos 2 theta by 4n. Okay, so you can kept a imaginary crank which is induces centrifugal force, okay, that is mr 2 omega square by 4n. Okay, along the line of stroke you will have cos 2 theta term will come into the equation, mr 2 omega square cos 2 theta 4n. If you put the some mass, okay, with the orientation of 2 theta, then you will have okay, 2 theta, then centrifugal forces of this mass is mr 2 omega square by 4n as per our equation, this one. Okay, and the horizontal component of this is cos theta term will also come along with the mr 2 omega square cos 2 theta by 4n. This horizontal component only the force along the line of stroke, which is, okay, if you kept the mass of crank length r by 4n at rotating imaginary, you can imagine that it is rotating with 2 omega and kept at 2 theta angle, then this is balanced horizontal component. Of course, there is a vertical component remain unbalanced. Okay, so the balancing component is this one. Okay, thus the effect of secondary force is equivalent to an imaginary crank of length r by 4n rotating at double the angular velocity, that is twice the engine speed. Okay, then this imaginary crank coincide with the actual at the inner top dead center. Inner top dead center means theta equal to 0 crank angle. At theta equal to 0, these both will maximum mr omega square, okay, by omega square. At the other times, it makes an angle with the line of stroke equal to twice that of the crank. I think you are able to understand. Okay, so the secondary couple also similar way, two cylinders and a secondary force leads to secondary couple about a reference plane, that is center line, is given by the multiplication of the secondary force with the distance between them. As primary force couple we have written, that is okay, plus or minus 1 by root 2 1 minus c mr omega square into L. Secondary is similar way you are getting, maximum is r is replaced with r by 4n, omega is replaced with 2 omega, okay, 2 omega whole square. So that secondary couple also you can write equation, similar equation. So these are all the about secondary force, that is secondary force, how do you analyze, tackle, and that is how much mass you need to keep at the crank and m, and at what radius r by 4n, and angular velocity is 2 omega, and angular inclination of that crank is 2 theta. Then horizontal component is will be balanced, and there will be a again same problem, vertical component of that, it leads to hammer blow. And similarly couple, okay, this force balancing you have done all right, but vertical component leads to couple, the secondary couple about a reference plane, that magnitude also you can write as similar as this one, primary couple, but the way you need to write is replace with r place r by 4n, omega place 2 omega. Okay, that's all. Okay, about this secondary couple, secondary swaying couple, secondary tractive effort, and primary swaying couple, primary tractive effort. and hammer blow, you know that magnitude of vertical component of any of these. Okay, these are all about the effect of unbalancing, effect of partial balancing of locomotives. So with this, this is the about the analyzing part of the unbalanced or partially balancing locomotives. In coming lectures, we are going to see numerical exercises on all of these concepts one by one. Okay, with this I am concluding this lecture. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.